Hello, it's semester 1, 2023, and this is a revision seminar, probably more like a workshop, for Algebra 2. I'm going to make an attempt to record something useful. What we're going to do is we've got a beautifully donated set of notes, and we're going to find things to talk about from early in the course, and then if we're really lucky, we may make sense of tensors from the very end of the course. That's the plan. All right, that's the plan. So flicking our way through the course so far, and we started with partitions and equivalence relations, which are fun. And I have a question: why are equivalence relations in this course? Yep, because you're going to officially use them when you get to cosets. So also a lot of your group operations are done on a thing that has an equivalence relation on it. So when you do modular arithmetic, that is in this course, isn't it? So when you do modular arithmetic, and you do things like 3 is equivalent, does he use a triple equals? Yeah, 3 equivalent to 4 mod, not 4, 13 is equivalent to 4 mod 9, for example, that sort of thing. You're setting up an equivalence relation there, so that the number 13 is considered to be the same as the number 4, and you're creating a partition where anything in the collection of things that are 4 more than a multiple of 9 are considered to be the same thing, but you're not really. So when you do cosets, that's what you're doing as well. And so so when you do like 3 plus 7 is 10, which is 1 mod 9, and we start writing things like 3 plus 7 equals 1 mod 9. Officially what you're doing is you're saying the set in the partition with representative 3 plus the set in the partition with representative 7 is equal to the set in the partition with representative 1. That's the idea behind it. It's officially what you're doing, but most people do not think about it that way ever. You just say, well, I can replace 10 with 1 at any point because it's the same mod 9. But that idea of an equivalence relation of being able to replace one thing with another thing at any moment is what that's for, and it gets used when you do, as you say, cosets later on. So that's why that's there. Cool. Plus, you get some practice early on in the course in proving more or less random things. And so it's a nice little thing that you can do to prove things. And I personally love equivalence relations. I love that there's the rule that only uses one object, and the rule that uses 2 objects, and the rule that uses 3 objects. And so it's like reflexive is A, transitive is A and B, and so symmetric is A and B, and transitive is A and B and C. Kind of like that. And this one has no conditions, but this one has this implies this, and this one has 2 conditions implies this, and so it appeals to me from an aesthetic point of view. Anyway, yeah, this thing here, officially it's the set that has 5 as its representative, which is 5 bar in this thing here, but we don't ever write it that way most of the time. Okay, and then we have groups. And we're all familiar with the definition of a group, and is that embedded in your mind without having to look it up? All right. You're going to help me because this is for you. It's good to try and remember it. What is the definition of a group? Okay, so G a set G with a binary operation. Yep. I have a question. Does binary operation, the definition of binary operation in this course, no, does not necessarily imply closure. Fancy. Okay, so you've just said it's closed. That is rule number 0, according to your lecturer's list. And what does closed mean? So if A and B are both in G, then A dot B is in G as well. All right. Another rule. Someone else is going to tell me one. Associative rule. And what does the associative rule say? I'm just going to repeat that here. The brackets don't matter. That's what you're doing. I love it. It's this. Like that. You can see where the brackets from here went there. They've flipped over the B to the other side. It's very visceral and kinesthetic. I love it. For A and B and C in G. That's the associative law. Okay, cool. Next rule. Inverse and identity. Officially, you have to have identities before you have inverses. It distresses me that he didn't call the identity rule G1, because 1 is the identity for multiplication. That would appeal to me. And how does the identity go? Okay, so you've said E times A is the same as A times E, and these are both equal to A. Yeah, I just, for my own purposes, would like to write them both here. Okay, so what is E? That's the identity. All right, so you have to say there is an element E in G so that E times A is A and A dot E is A for all A in G. So these ones require, these ones are things that happen to no matter what A, B, and C are, and this one is specifying the existence of a particular kind of element. And that's called the identity. And you said the other one was inverses, Isabel. So for any A in G, there is A dashed in G so that A times A dashed is E and A dash times A is also E. And it doesn't have to be times, it could just easily be plus or anything else. But it's tradition to write them as multiplication if you don't know.
Is the inverse unique?
That's a theorem, actually. So yes, the inverse is unique, but you don't actually have to, it's not part of the axioms that it is unique. So you can be sure it's a group without knowing that the inverse is unique, but once you know it's a group, the inverse will indeed be unique after all. Does that make sense? Okay. Cool. And so that's your classic original recipe group. And then there's a little extra spice. If you have the commutative law, then you call it an abelian group, after mathematician Abel. And that's called the commutative law. Okay. Yeah. So that is what groups are. And so you really do need to know that definition. And you did. It was all there. You just had to pull it out. And it's nice that they have names. This is... it's nice that they all have names. Being closed seems stupid. Like, why would it produce answers that aren't in the group? But that's important for making subgroups. So a subgroup is a group that is a smaller part, well, not necessarily smaller, but a part of another group that is self-contained with respect to the operations that you do in groups. So it has to contain the identity, it has to contain all the inverses of all the things that are in it, and it has to be closed under multiplication. Yeah, it has to work as a group under its own right if you remove the rest of the group. Exactly how subspaces work in Maths 1b. They're self-contained. And in fact, a subspace in Maths 1b is a subgroup under addition. But more than that. So, yeah. Okay. So, what do we know about groups other than their definition? It's like 5,000 theorems, right? And there's classic groups, right? Oh, look, there's a list of classic groups here. Classic groups, the integers under addition, the integers under multiplication, not a group, but if you remove 0, then I think still not a group, because they don't have inverses. Yep. The real numbers without 0 are definitely a group. And so your lecturer uses R star, and then sometimes uses star in other contexts to mean other things. Cool. The matrices of the same size under addition, all the matrices that are invertible of the same size, they are a group 2, but it's not an abelian one, and that's our first non-abelian group so far. And then Zm, which is Z under addition mod m. Yeah. And Zm star under multiplication if m is a prime number. That'll work. So there are classic groups. We're doing well. And symmetries of things. So a way of rearranging things in such a way that they look the same as they were before. Cool. Oh. The symmetries of the regular n-gon is called the dihedral group on n vertices and denoted dn. So we've got some classic groups here now, right? So we have Sn is all the symmetries, like all the permutation of n things, is that right? And Zn, which is the integers under plus mod n, well, integers mod n. And d, yep. That's a great question. I'm going to repeat it. When they give you Zn, how do you know if it's plus or times? Context will tell you. If the operation they write down is plus, then it's Zn under plus. Yep, so we do know that Zn under times isn't a group. In fact, Z under times is definitely not a group. So just a second, just while we're here, Zn under plus group, Zn under times not a group. Yeah, so 0 doesn't have an inverse because there's no way to multiply 0 by something and get anything other than 0. Yep. Zn star under dot is a group if n is prime, and not if n is not prime. Because in a group, because it's not closed, if n is not prime, then you can get two numbers and multiply them together and get 0 as the answer. So in Z12, 3 times 4 is 0, because it's 12, which is 0, and so it's not closed, therefore, which is kind of cool, actually. But if it is prime, that is a group, which is cool, which means that Zn, where n is prime, is a field, which they define. Do they define that in this course? Yeah. They do the field? You have to have fields in order to have vector spaces, so they must have said it somewhere. Okay. And things that have both addition and multiplication tend to be rings, and there's a whole course in third year about rings and how they're related to the groups that they're related to. So that's the integers mod n. So here we go, we've answered our question. If they just say Zn and they're telling you it's a group, it must be plus. Yeah. Awesome. And the operation in this one is doing them one after the other. It's composition as functions, because when you say a permutation, it's officially a permutation is a function that takes the list in and spits out a new list. Actually, it's not even that. It takes each individual element in and spits out a new element, and it's a one-to-one function and onto. So, sorry, bijective. That's the fancy word for it. Yeah, I take C.S. Lewis's approach, is that in some when you become older, you put away childish things, and when you become even older, you stop being afraid of childish things. Yeah. I think it's the snobby word, actually. It's the Bourbaki group who just went, we want to be snobby and make all our mathematics snobby and use fancy words that no one else uses, because that means that we're in the in crowd if you're using those words. But when people invented the concept of one-to-one and onto, they used those words. In French, but still. Yeah, anyway, that's my first. I despise calling things grown-up things. Some things are grown-up things, that is the truth, but grown-up means not appropriate for children, in my book, because as a parent, that's what grown-up usually means. Okay, and then there's the Dn, which is the symmetries of a regular n-gon. Okay, classic groups, cool, cool, cool. Oh, the Klein 4 group. What's it called? V4? Did Raymond tell you there used to be a band called the Klein 4 group? It had 4 members. I don't know if it was a good band. And so that's the symmetries of a rectangle And these ones are all subgroups of Sn, because you can pitch them as, by labeling the corners, you can pitch them as permutations. Cool. And so far, I think that's our list of classic groups so far. Oh, there was this one, the matrices, right? Damn it, not enough room. So even though you're not allowed a cheat sheet, like having a cheat sheet would actually be cheating in this exam, it's not the worst thing to make one, so that you can see all of these things in one place. Yeah. Or since you don't have to take an exam, you can make it as big as you want. Nice big bit of butcher's paper with everything on it all in one place, so you can see it all at once. That would be cool. You know, all the classic meme of all the papers with the strings and stuff. Yeah. Okay. So what is it? M. Did he actually write M comma N? Did he? Oh, he said N. Something like that. I've got a 1 here, but I think this is it. And GLNR, N by N invertible. So this one isn't, this one has to be under multiplication because it doesn't have an inverse for addition, because the zero matrix isn't invertible, and so it's not a group under multiplication. It's not a group under plus. And this one is under plus, it's not a group under times. So there you go. It looks like you don't have to specify the operation because it's not a group under the other option for what the operation could be. That's the important thing about them. So when you say Zn as a group, has to be addition because it's not a group under multiplication. That's a useful question to answer. Cool. And then we made so here we are. There's the theorem you asked. Are the inverse is unique? Yes, every element has a unique inverse. And so this is the game of pure mathematics. You go, what are the axioms? What's the smallest list of things that we need to be true in order to make it whatever the thing I want it to be? And everything else is a theorem based on those axioms, or a lemma, or whatever you want to call it. So it is definitely true. Some truths are that the identity is unique. Inverse of each element is unique. And then this other theorem has like A times B. If A times B equals A times C, then B equals C. So you can cancel out from the left side and cancel out from the right side. The reason why we care about this is it's a shortcut. You're allowed to just do this now. These are truths. But also, if you would like to make something that was almost but not quite a group, then maybe you would have something that satisfies the cancellation laws, but doesn't necessarily satisfy the associative law, for example. And that would be called a loop. I did loops in my honours project. Thoroughly annoying to live in a place where the associative law isn't true. It's really weird. Don't go there unless you've braced yourself for the weirdness. And so those are the truths. And so there are lots of truths, and in fact we get more and more and more truths as we go along with various theorems about the sizes of subgroups, basically. How do you feel about cyclic groups? What's that? Something has a generator. What does the word generator mean? Ah, okay. So cyclic groups, you're telling me, are this sort of thing. And so that is the identity and A times A and A times A and so on until hopefully you get back to the beginning, but it could possibly go forever. Yeah, okay. Where A squared means A times A and A cubed means A times A and so on. So cyclic groups, so this is what they look like if the operation is multiplication. If the operation is addition, you'll have like A and 2A and 3A and 4A because you'll be adding them together instead. And cyclic groups are automatically abelian. Cyclic groups are great. Zn is a classic cyclic group because it's the, under addition, and so it contains 1 and 1 plus 1 and 1 plus 1 plus 1 and so on until you get back to the beginning. So one thing that's confusing about groups is that most of the theorems are written as if the operation was multiplication, but if the operation is addition, you have to bend your mind a bit and treat the powers of things are actually just numbers of things. So I think we're getting very close here to a couple of theorems about groups, which is that the size of a subgroup has to divide the size of the group. In G, and it's called the order, isn't it? It's called the order of G, I believe, that thing. Because in my head it's just the size of G, the number of elements that G has. And if H is a subgroup of G which is finite, then the order of H divides the order of G. Which means that if a group has a prime number of elements, it doesn't have any subgroups other than just the identity all by itself, because nothing divides into the order. Yeah, so corollary like that. But also, you can talk about an element having an order as well. And so the word order for an element, the order of element A is the smallest n such that A to the power of n is the identity. like that. And if no such n exists, it's infinity, I believe. Yeah. And it actually happens to be that the order of A is the size of the cyclic group that A generates. Yeah, because the idea is you start with the identity and then you just keep going until you get back to the identity, and so the number of elements it takes to do that is the order, which is the same as the size of this group. And so therefore, order of A divides the order of G as well. And in fact, if you do have a cyclic group, every order of an element actually exists in a cyclic group. So I'm sure there's a theorem somewhere. So just an example, cyclic group of order 12, for example, which would be basically Z12 will do the trick. That's a cyclic group of order 12. Every possible divisor of 12 exists as the order of an element in a cyclic group. Not true in every other group, but definitely true in cyclic groups. And so we have 1 has order 12. It takes 12 times to add it to itself to get back to 0. But 2 has order 6, and 3 has order 4, and 4 has order 3. And 6 has order 2, and 0 has order 1. Because you don't have to add it to itself any time. Like, you don't have to add it to itself any times to get back to the identity. It's already the identity. So, yeah. And so these are all the divisors of 12. And so every number has an element that does it. Yeah. 8 has order 3 as well. Just while we're at it, we should have done this here. 5 has order 12. It takes 12. You have to add 5 to itself 12 times to get to a multiple of 12, because 5 doesn't divide into 12. And 7 has order 12, and 8 has order 3, and 9 has order 4, and 10 has some order. I reckon 10 has order 6, I'd say. And 11 has order 12 again. And so they all have different orders. And only some of them have order 12, and those ones can be chosen as generators for your cyclic group. So it is possible, therefore, for Z12 to be generated by 1, but it could just as easily have been generated by 5 or 7 or 11, for example. Yeah. This is the best one, but any of these is fine. Yeah. And all cyclic groups work that way. They're all the same as Z whatever, the cyclic groups. There's a theorem there somewhere. And that is called isomorphism. When we say that a group is the same as another group, it means that all of the structure of which thing when multiplied produces which thing is exactly the same, they've just got different names. And so is that what that's what it means. But what's the definition of an isomorphism? Is that, do they still call it an isomorphism? So an isomorphism, so let's see. Function, traditionally phi, isn't it? Is that how they do it? Yeah. Which sends G1 to G2 isomorphism when it's bijective. And when you do the operation in G1, when you multiply G and H in G1 first, and then do the operation, you get the same answer as when you do the operation first and then multiply in G2. You get the same answer. So this times is in G1 and this times is in G2. And that's called an isomorphism, which means exactly the same shape. Iso means exactly the same, and morph means shape. And a homomorphism is one where it doesn't necessarily have to be bijective, but it still does this job. Have I got that right? Just guessing. So Jasper is saying the first isomorphism theorem. What does the first isomorphism theorem say? I wish they didn't number them. So you're saying that we have a homomorphism and you get the kernel of phi. Is that how they write it? Something. That's okay. This is good for your memory. So the kernel of phi, you're saying that G is isomorph. Is that the symbol we use? Sure. Factored out this is the image of phi. So in order to understand the first isomorphism theorem, we need to know what all of these symbols mean. I'm hoping that that's the first one. Permutations, alternating groups, normal subgroups, cosets. Factor groups. Yeah, whatever. And there is only one isomorphism that does this. I think we need to talk about this. This is something we need to talk about. Okay. There are a lot of things going on in this theorem. And in fact, everything that's before this in the course is probably leading up to this theorem, because people love this theorem deeply. It means a lot to them. So, we need to know what the kernel means. So what is the kernel? Yep. Sorry? Sets it to the identity. Sounds good to me. So the kernel is the set of things that are in the first space such that phi of G is the identity in G. I need to draw a picture of this. Here's G. Oh, yeah, second space, you're right. Identity in the second space. And here is H. And here is the identity of H. And then a whole lot of things will all end up here when I do phi. And all of those things together, that is the kernel of phi. And you are guaranteed for the kernel of phi to have the identity of G in it. Right? And everything else in G will go somewhere. And when you collect together all of the things that come out of G, that is the image of phi. So the image of phi is the set of phi of G's such that G is in G. It makes me deeply happy that the kernel and the image are defined oppositely in the way that we use the set notation. This one says that look in G and then find the ones that satisfy this rule. And this one says make all of these things. And they're the two different ways to define a set with set notation. One is focus your attention on these objects, only pick out the ones that satisfy this rule, whereas this one says make all of these objects satisfy using this technical detail. Pardon me. And when you made subspaces back in Maths 1B, you could either define them as a set of points that satisfied a homogeneous linear equation, that's this version, or the span of things, that's this version. And so that appeals to me a lot, that they are the opposite ways of defining a set. So the important thing about the image is it's part of H. And an important thing about the kernel is it's part of G. So the kernel lives in G. It's ones that started here and they all end up, all of the entire kernel ends up here at the identity of H. And the image lives in H. It's all of the answers for my function. So there may be things in H that aren't in the image. It's possible that there are things in H that don't come from anywhere in G. They're just there. They're just there. But everything in the image does come from something in G. And in fact, what happens is if there were 4 things here that all came to the identity, then everything here would have 4 things that went to it as well. It all adds up neatly. I just want to point something out here. So suppose G had these 16 things here, and H was made of however many things it's made of. I don't care. And this is the identity of G here. Let's put it in the corner. And this is the identity of H here. Suppose all of these things ended up here. Like that. And so this is the kernel just there. Then what's going to happen is that because it is a homomorphism, I know to get from any one of these to any one of these, I can multiply by something, if it's a multiplication group. And so what's going to happen is that all of these will all end up at the same place, and all of these will all end up at the same place, and all of these will end up at the same place. And so I'll get an image like this. And so what I'll end up with is all these copies of the kernel inside G, they are cosets. So this is what the theorem is about. It's saying that if I, not that we have a meaning for this yet if you haven't done the course, if I divide out the kernel, if I cut the group into pieces of size kernel, I will get the number of pieces will be the size of the image. That's one of the things that it does. So it's not just about sizes, it is about sizes, but it's not just about sizes. So we definitely know the size of G divided by the size of the kernel will be the size of the image. Because, yeah, all of this has to be squashed into the image, and they'll go the same number of each. 4 will go here, 4 of them will go here, 4 of them will go here, 4 of them will go here. And if there were 5 that went to the identity, all of these, everything that was in the image would have 5 things that went to it. And that's just really useful to know. They're all the same size. But it's not just that they're the same size, the group operations are the same too. So we need to know what it means to be a factor group. That's a factor group there, right? That's what they call it? Quotient group? Sure. I learned it as a factor group, but it's fine. I'll be okay. Quotient makes more sense from the way that we write it, because quotient is a fraction. So your quotient group there, but they do call it factoring out, don't they? Yeah. Yay! So this that thing's called a quotient group, but the action that produces it is called factoring. Awesome. Awesome. Okay, so we need to know what that means to make a quotient group. And what it means to make a quotient group is this first. We have to cut the group into pieces of size, whatever this is. And it only works if the thing that you're quotienting, the underbit of the quotienting thing is a normal subgroup. Oh, so crap, now we've got even more notation that we have to talk about. So H is, wait, just a second. These things here, they're called cosets, like that. So here's the thing, in any group, this is an extremely random ordered revision seminar. Don't forget the rule that you can ask questions at any moment, okay? Even if it's just mildly inspired by what we're talking about. The idea of a group of thing is that if you have a subgroup, this is G and this is H, and that's a subgroup. And being a subgroup means that you can't escape H by doing the group operation on things in H. You just produce more things in H. No matter which two things in here, if you multiply them by each other, you'll get another thing that's inside H. That is how H works. So H is nice and self-contained. These two things multiply or add or whatever it is the operation is to produce another thing inside H. That's great. And when you have an inverse of any one of them, it produces something else that's also in H, and that's beautiful. But if you multiplied anything in H by something that wasn't in H, you would end up somewhere else entirely. So one of the ideas of how cosets work is that if I multiply everything in here by something else, so this is A and I'll have A times G, and this is B and I'll have B times G, and this is C and I'll have C times G. When I do that process of multiplying everything by the same number, I will produce a whole extra set that doesn't overlap with H if the G isn't inside H. And in fact, if you multiply the identity by G, you will get G. So if you pick something that isn't in H and you multiply everything in H by G, you have to produce a set that doesn't overlap with H at all. and you could put the g on the other side, and it's tradition to do that. Sorry about that. So this is called h times g because I got it by multiplying by g on the right-hand side of all of the things in h. And then this might be g times h times something else. K, right? Something else. And this has got a k in it. And what happens is that if I multiplied h by something else, it would end up in one of these two things in this particular picture. But your group might be bigger than that. There might be lots of them, right? And it would have to fall into one of these. And these things are called cosets. And these are called right cosets because I got them by multiplying on the right-hand side. But it is possible for the way that your group works to multiply by on the other side and get whole different sets. Well, I'm going to do this. So that's G, and this is H, and there's the identity there. It has to be inside there. It could be that when I make the left cosets, I'm going to draw them in green. I make all these left cosets, but if I do the right cosets and multiply on the other side, so this one's going to be like G times H, and this would be some other G times H, and this would be some other G times H, and this would be some other G times H. It could be that if I multiply on the right-hand side, I get something else entirely. Like that. And so I've got GHs and HGs, for example. Actually, HG and GH would have to overlap, sorry, but that's okay for a particular G. So it could be, so you will, no matter what, if you make all the cosets by multiplying H by all of the things in G, you will make a collection of cosets. If you multiply on the left-hand side, you'll make one collection of cosets, and if you multiply on the right-hand side, you'll make a different collection of cosets, and both collections will cover the whole of G, but they might cover the whole of G in different ways. And that would be not as productive as we would like. So in this one, the left cosets not all the same as the right cosets. But if it turned out that all the left cosets were also equal to this, so that is one way that the left cosets and right cosets could be different, but it could be different again. It could be that this is H, and this is G of H, and this is K of H, and this is H of K, and this is H of G. No, that won't work. No, won't work at all. Sorry. That doesn't work. It's okay. G of H and H of G have to share G. There is no way around it. They have to share at least one thing. Okay, just want to point that out. I'm drawing pictures now because I like to draw pictures. If this is H, and this is G of H, then H of G has to share at least something. They have to share a bit because G itself is in G of H. Because if I multiply by G, multiply the identity by G, I will get G. And so it has to be in both of them. So they will overlap by a bit, but they might not overlap totally. But if you're very lucky, G of H will be the same as H of G, and K of H will be the same as H of K, no matter what G and K are. And so this is called H being a normal subgroup of G, which is notated by this, I believe. Is that right? Let's stop there for a moment. How are we feeling about what I was doing there with my pictures? Yeah. I'm very proud of this. This is my first inspiration for being able to draw this in such a way that makes sense to me, with the triangles being the other way around. I kind of like that. Makes sense. Whereas this one, not so easy. You can do them that way, but the triangles were fun. They were fun. Okay. So one of the things about cosets is that all the cosets will be the same size. They'll all be exactly the same size. If H has 4 elements, all the cosets will have 4 elements. And it's the existence of cosets which causes that theorem about the sizes of the orders of groups to be true. And the reason they're the same size is that the only way that is that if you multiply H by everything by the same G, you have to get all different elements, because if any 2 of them were the same, then 2 of the elements of H would have been the same because of the cancellation law. So we can have a proof that that cosets are all the same size. So consider G of H, they're all the same size as H, which is the set of things that are G times H, where H is something in H. So you take all the elements of H and you multiply them all by G, and you get this thing called GH. It can't be smaller than H, like it can't be bigger than H, because we only started with the size of H elements to begin with, and we multiply them all by G, so there's got to be, at most, H of them. So the size of GH is definitely less than or equal to the size of H, because every one of them came from one of the elements of H. So definitely that's true. And the only way that G of H could be smaller than H would be if 2 of them were the same. I'm going to come back to that, Jasper. Because if they're all different elements, it has to be the same size as H. And so let's just say, suppose G of H1 was equal to G of H2. Oh no, we had a cancellation law from that theorem earlier, and therefore H1 is equal to H2. And so actually they are not different elements at all. Yay, there's a one-to-one correspondence between elements of GH and elements of H. They are the same size. The relationship H goes to G of H is 1-to-1. And therefore they are the same size. Cool. So this bit here is probably not important. It's this bit here would be the proof. Yeah. Woo! Okay, cool. So since the cosets are all the same size and they cover the entire of G and they partition the entire of G, therefore G must be made of several sets of things that are all the same size, and so therefore that number must divide into the size of G. Yay, beautiful. Okay, so I've just been asked, is it true that just a second. Is it true that if H is a normal subgroup, then the group operation has to be abelian? No, it does not have to be true. So if G is abelian, then definitely any subgroup H is normal, because it doesn't matter what side you multiply anything on ever. But it is possible for H to be normal in G even if G is not abelian. But I do think something has to be abelian, and I think it's the multiplication in the quotient group has to be abelian. It turns out that way. Pretty sure. Could be wrong. It is definitely not true that if there is a normal subgroup, then G is abelian. And I'm almost certain, I'm not 100% certain, I'm almost certain that if all the subgroups are normal, then it does have to be abelian, but I think that may also be false. I think it is possible for all the subgroups to be normal, but still the group operation not be abelian. Could be wrong. But my instincts are not good there. That would be a great thing to Google. I reckon there's a theorem, there is either a theorem that says that all the subgroups being normal means that the group operation is abelian, or there's a counterexample somewhere. Pardon me. Do we know it? Did you look it up? It would be like a Tuke question, I reckon. Prove that if all the subgroups are normal, then the group is abelian. No, it doesn't have to be true, because what if all the subgroups are just the identity? Ah, yes. Just a second, just an aside. If all subgroups are normal, is G abelian? And the answer is no, because consider Z7. Not Z7, that's not an abelian group. Damn it, that is an abelian group. Curses. Well, in my head, I don't have a proper example, but consider a group G with, and maybe I'll just pick a nice big prime number. Oh crap, I could be wrong. I was trying to pick a big prime number, and then we know it doesn't have any subgroups other than the identity. But I think a group of prime order has to be cyclic, actually. I'm pretty sure. Oh, then, and if it's cyclic, it's therefore abelian. Oh, I thought I had it. Sorry, I have no idea. I don't know. Nope, I don't know. I'm really sorry. Permutation group's not abelian, right? No, it's not true. So they tell me that if all the subgroups are normal, it can still not be abelian. The Hamiltonians under addition? Huh. So the Hamiltonians are what I would call the quaternions. Yeah. Hamiltonian star under multiplication, maybe?
It's a group for which all the subgroups are normal is the defined group, and none of them want to call
Q8.
Yeah.
Oh. Apparently no. So you're saying that Q8 is a group with that has all normal subgroups. And order 2 have to be subgroup.
normal.
Right. Yep.
I just found one of the practice questions is like finding subgroups and showing subgroups. So yeah.
I told you there'd be a tutor practice question about it. So what's Q8, by the way? How do you define Q8? What?
Yeah, he defines it in terms of
Oh, cool.
so he has E equals the identity matrix, I equals like going from 0, 1, negative 1, 0, yeah, like that, and J is equal to 0, I 0.
With complex numbers?
Sorry, yeah, complex number. And K is equal to I 0, 0, negative I. And Q8 is equal to plus or minus all those instead.
Oh, wow, cool. Q8 has all of these things and their minuses. Oh, okay, so you're saying that it is 1 and minus 1 and I and minus I and J and minus J and K and minus K from the quaternions. Where I times J is K and J times I is minus K and all of those things. Yeah? Huh. Wow. Cool. And so you're saying that all of the subgroups have order 4? Or they're all order 2? Okay. But they're all normal. All right. Nice. Cool. And this is under multiplication. Wow. Well, there you go. Well, we have an answer. I don't think they expect you to remember what Q8 is. I don't think Raymond would expect that.
No, I think they'll do anything about their fine, because they think it's
Yeah. All right. Wow. So it's got order 8, and so it can only have subgroups of order 1, which is just the identity, order 2, which would be the identity and I and the identity and J and the identity and K, and order 4, which would have, there would be some of those, and the entire of Q8, because they're the only numbers that actually divide into 8. Nice. Okay. Fascinating. Deeply fascinating. Wow. Just bear with me. So the subgroup generated by I has 1 and I, and then, oh no, Would be that, wouldn't it? Multiply by I again, you get -1, multiply by I again, you get -I, multiply by I again, you get -1, which is 1. And so the coset, if you multiply that by j times that coset, so j times that subgroup is the coset j, and that would have j and j times I, which is -k, and minus j, and minus j times I, which is k, and you would get this thing is the other coset, and that contains everything. But if you multiplied by I times j, you would get j, I times j is plus k, minus j, and minus k, which is the same thing. Okay, so all the cool, all right, nice. I mean, there's only enough space to have, like, all the cosets, no matter what they are, can only be this other thing. Because there's the cosets that aren't the group itself can only be the rest of the group. And so if your subgroup is half of the group, it has to be normal. That argument there. Oh, that's a cool fact. So if the size of H is half of the size of G, then H must be normal. Yeah, because there's no space to put its cosets other than that one spot, which is the rest of G. Nice. Well, that's some fun stuff going on there. Okay. So, where are we? We've got normalness. So if it is normal, then you can create this quotient group. Yep. Okay. So if H is a normal subgroup of G, so is it true that if I just write a less than sign, it means is a subgroup of? So just as an aside. H is a subgroup G. And H is contained in or equal to G means H is a subset of G. Okay, cool, just making sure that I'm got all the notation. So if H is a subgroup of G, then you can make a group out of the cosets of H. Is a group under its own little multiplication where GH times KH is the new coset by multiplying G and K H, like that. Is this meaningful to you? Like this is defined to be this, right? Yeah. So this is the name of a set, GH, and this is the name of a set, KH, and we are going to define that when we multiply those sets together, we get the new thing with this name of the set, which is GKH. Right. And it does actually work. If you multiply everything in here by everything in here, you will produce this set. But that it does actually work as a multiplication thing, but there's no particular reason it had to work. It's just a notation. Yeah. Okay. Cool, 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 cool. And so what that means is that when I drew this picture back here, one of them, these are cosets, and if this really is a normal subgroup, then multiplying these two together might produce that one, for example. And multiplying this one and that one would produce that one, and maybe multiplying these two together produces that one. There's a multiplication of the groups as a whole, And I'm pretty sure it turns out that if you multiply any one of the things in here with any one of the things in here, it ends up with one of them in the other ones. That's how the matrix, the multiplication works. So when you do the group multiplication, if GH times KH is indeed GKH, then G times H1 times K times H2 will be G times K times some H3, basically. That will be the truth, no matter what H1 and H2 are. Yep. It doesn't have to be abelian to do that. This is just a magic trick it performs even if it's not abelian. If it's abelian, then it'll totally work because you can just switch this K and this H here, but it'll work fine even if it's not abelian. If it has normal subgroups at all, which it might not. Okay, cool. And so we make a group out of the cosets, and the theorem asserts that the group that the cosets behave by is the same shape as the group that the image is, because the image is also a subgroup of H. So that's another thing that we didn't say. The kernel, so what the theorem is saying, which says that if phi sends G to H is a homomorphism, then the preview to the theorem, which is probably a lemma, says that the kernel of phi is a normal subgroup of G, and the image of phi is a subgroup, not necessarily normal, is a subgroup of H. And oh crap, the set of cosets is a group, and it's called G quotient H. That is the name of the group made of the cosets. So it's made of an entirely different thing from what the elements of G is made of. It's made of sets. So that's what the theorem says. So these are previews to the theorem. They're not technically part of the theorem, but they can't be true. The theorem can't be true unless they're true first. And so if you make a homomorphism, you are guaranteed for the kernel to be a normal subgroup of G, and you are guaranteed for the image to be a subgroup of H, and you are also guaranteed that when you do the quotient subgroup by making the cosets of the kernel, you will get the same subgroup, you will get the same shaped group as the image of phi, which is what this diagram here was trying to get at. Not only are all the sizes matching up, but if I multiply this coset by this coset and I get that answer, then that will guarantee that multiplying this by this will get that answer as well. Yeah, and so on. Now, all of the structure of multiplication here is copied here, and vice versa. It works backwards just as much. Yep. There you go. Cool, huh? So the big thing that they normally do with this is to prove that that Z, like 4, for example, is actually the same as the factor group of Z under the homomorphism that goes Z goes to Z. Like you can do this. Phi sends Z to Z by phi of n is 4n, for example. And this is a homomorphism. Phi of n plus m is 4 of n plus m, which is 4n plus 4m, which is 5n plus 5m. So this is definitely a homomorphism. If I do the operation in Z before I do phi, I get the same answer as if I do the operation in Z after I do phi. We're used to it being multiplication, but it does work for addition. And so we are interested in what the kernel is. The kernel of phi is the set of things that are in Z such that phi of n is 0. And 5n being 0 means that 4n is not 0. Yep. I've done something wrong. Just a second. That's right, isn't it? Is equal to the identity in Z, which is 0, right? Okay. Bear with me. Oh, crap. I really thought I had it. Well, it's definitely homomorphism. And the image is definitely all the multiples of 4. Right? Which is not the same as Z. Well, maybe it is. Oh, it is. It is. No, it's not. Because the cosets. No, I think I've got this upside down. Maybe. Could be wrong. I was really trying to make Z4. That's what I was trying to make. Oh, I'm factoring out the wrong thing. That's okay. That's all right. I was doing this wrong. I'm going to keep going and then try and get the one I really wanted. And that means that n equals 0, which means that the kernel of phi is just 0. Which is the trivial subgroup. It's definitely closed under the operation. And the image of phi is phi of n such that n is in Z, which is equals the multiples of 4. Yeah, which you normally call 4Z because that's the notation for it, yeah? And so therefore, Z factoring out just that is isomorphic to 4Z. And this is isomorphic to Z, actually. So which makes sense, I guess. If you add two multiples of 4, then whatever multiple of 4 they were, you'll just add those two numbers, and it works fine. Okay, that's okay. I'm all right. So the cosets of the identity are just single numbers, right? Like if you multiply the identity by, well, add things to the identity, you will get just the thing. And so, yeah. Okay, that's not what I wanted. Huh. Fascinating. So Z is isomorphic to 4Z, but Z quotient 4Z is isomorphic to something else entirely. I wonder what the homomorphism is that has as its kernel the things that are the multiples of 4. I don't know if there is one. Is there a homomorphism which sends phi from Z to somewhere, I don't know where it is, so that the kernel of phi is 4Z? Ah. Ah.
That was one of the assignment questions, was basically like, what is this?
So just take a notice, wait, I've got something. Z under plus to the complex numbers under multiplication, without zero under multiplication, that's definitely a group. That's definitely a group. And then you could have phi of n is going to be e to the n times pi on 2 I. That. Yes. Because that can only produce these 4 numbers on the complex plane. Because e to the 0 is 1, and e to the pi on 2i is there, and e to the pi I is there, and e to the 3 pi on 2i is there, and you can only produce these numbers. Yes. Yes, and so the kernel of phi is the set of n's in Z such that e to the n pi on 2i is 1, because it's 1, the identity is 1 in this thing here. And so e to the n pi on 2i being 1 would be, that's 2 pi k, like that. And so you would need n would have to be 4 times a multiple of would have to be 4 times something. Yes. For any k and z, for k and z, and so therefore the kernel of phi is the set of numbers that are 4k times k and z, which is what 4z is. Yes. Yes. And so by the homomorphism theorem, z out of 4z is isomorphic to the subgroup which is made of these things. Yeah. Which is isomorphic to Z4. Because it's a cyclic group. Yes, which is generated by e to the pi on 2i, which is just I. Ah, cool. Thanks, previous tute/assignment question. So I can begin to feel your worry about this exam, right? Because that particular thing there required us to have collectively among the 5 of us an inspiration based on something we saw before once. And so I can feel the worry about this exam coming from that 5. Oh, which one was that? Oh yes, if all the subgroups are normal, does it have to be abelian? And the answer is no, because look at this wonderful random example. Yeah. I believe it's isomorphic to like Z2 cross Z2. No, that doesn't work because that would be abelian. No, it's something else entirely, isn't it? But everything's order 2 in V4, right? Yeah, all the elements are order 2. Yeah, but it's not abelian. Yeah.
That's what it's isomorphic. It was isomorphic before.
No, D4 is the symmetries of a square, which has more than 4 elements. D2?
There's like questions like that where it's basically like, oh, you have to kind of like remember how many types there are. It might ask you what's another group of this size unless you can think back to the different types there are, you don't say anything to.
So it's a little bit like trying to remember all the names of all the people in Downton Abbey. Sorry, it's just same thing, right? We've got all these characters that we've met once, and you're supposed to recognize them when, yeah. Just checking, a simple group doesn't have any subgroups? No non-trivial normal subgroups. Oh crap. So not having any subgroups at all other than the identity would cover it, but there are more things than just that. Oh wow. So it might have other subgroups, they're just not normal. Oh. The only simple groups I know off the top of my head are the cyclic groups of prime order, because they don't have any subgroups other than the identity. Okay, so simple means no non-trivial normal subgroups. Okay. And so examples are cyclic, like ZP for P prime, because it doesn't have any non-trivial subgroups at all, so they can't be normal. And the other one was A5, you're saying? Which is the even permutations on 5 things, yeah? Okay.
But it's like this was just wedged between some stuff about direct products and the first stuff. So it's like I don't know if I need to think about it sort of, or if this was one just like a thing he showed us about in one. And after the first isomorphism theorem, we moves to that stuff.
Oh, there it is there, it's on this page. What is this diagram for? It was Z cross Z. Is he trying to show that Z cross Z is the same size as Z? Oh, he's factoring out. Oh, okay. Yeah, they're the cosets. Okay, gotcha. So the span of 1, 1 is all of these diagonal, is all of those ones, and then the cosets will all be diagonal lines. Okay. Okay, cool. Wow. Well, I think a useful thing to do over the next, after you've, between the exam that is before algebra and the exam that is, and the algebra exam, at some point between now and your algebra exam is to just keep spending time talking to each other and to me, and we can figure it out. And your lecturer, if he's got options. He hasn't? Okay, cool. And me. And the other Maths Learning Centre tutors, but especially David, other David. I don't want that to be on the recording but it is now, because he might not be here forever, but I hope to be here for as long as I can. Just turn up randomly to his office. But be in the Maths Learning Centre rather often, and then he might turn up nearby. So, because if he still does consulting nearby. Anyway, I think a useful thing to do at this point when in your study is to find some of those things in the assignments and in the tutorials and whatever, and make sure that you can do them. And try to do them cold without looking at your notes. And a really important act would be to try and remember the definitions of things. Because even if you don't successfully solve the problems, trying to remember the definitions will be good for you as you go. Yeah. Well, that was a wide-ranging and interesting discussion. Didn't even get to vector spaces, but that was some group stuff.
So when you ask for the definition of a group, what are the actual axioms?
One of the few things I'm capable of remembering from second year algebra.
So it was like I could tell you something was or wasn't a group, but I'm struggling to actually recall that.
Well, I might stop the recording.